Alright, so in this video we will talk about quantum error correction. So now that we have completed our study on quantum algorithms, the next thing is to consider what happens if the environment becomes unstable and our quantum system becomes decoherent. Which is usually the case because so far we have worked with ideal systems. And when I say ideal, we mean that there is no interference from outside source, from external source, there is no distortion. But one obvious difference between a physical computing system and a mathematical model of computation is that mathematical models are immune to external distortions, which is not the case for physical computing devices. Physical computers or physical models of computations are subject to errors, right? So there are vast number of factors behind errors, but usually when we work with physical systems, they are more fragile. Okay, so especially when we work with quantum computers, in quantum computing, having a firm theory of error correction, quantum error correction, is inevitable because during the computation we will have interferences, we will have electromagnetic noises coming from external sources, and all these factors affect the performance and correctness of the computation. Now, suppose for a moment that our computation consists of t sequential steps. Okay, so t sequential steps, and that the success probability of each step, let's say it's probability p. But then the probability success of the entire computation then becomes p over t, assuming that p is between 0 and 1. So if p is actually equal to 1, then that means we have an error-free computation, which is not realizable. Okay, that's not a reasonable situation. And if it's equal to 0, then that means, well, basically our computation is always false. But let's suppose that p is strictly between 0 and 1. And if our computation consists of t sequential steps, then the success probability of the entire computation will be p to the power t. So it decreases exponentially as t grows. When we look at, so we begin with classical error correction, okay? Now, compared to classical computation, quantum computers are more susceptible to errors than the usual classical digital computers, because quantum systems are more delicate, they're more fragile. It's hard to stabilize quantum systems. The cooling and prevention from the electromagnetic fields and so forth. So if one day we have large-scale quantum computers having a firm theory of quantum error correction will be inevitable. Now, if we consider classical error correction, the most straightforward error correcting code is to repeat the state of the computer. So let's suppose that we want to protect our classical bit B, okay? So we start with classical error correction. Now suppose that B is a classical bit. bit that we want to protect. What we could do in classical error correction is to apply the repeating state solution. Repeating state. Repeating state is to repeat the bit that we want to protect 3 times. So if B is the bit that we want to protect, then we transform our bit, our physical bit, to a logical bit, a code word. So from B, we encode B into B by repeating the state B 3 times. Okay, so this is the code word. Code word for the bit that we want to protect. And then we introduce the code word through to the erroneous, to the faulty channel, and then we obtain a faulty code word, and then we apply a recovery procedure to obtain the original bit that we initially wanted to protect. So this is how an error correction procedure works. But this is very straightforward for classical computation, yet it might not be feasible for quantum computation for several reasons. One reason that we cannot use this repeating state solution on quantum computation is that we cannot repeat any state on quantum computation because we have the no cloning theorem. Right? So we cannot copy an arbitrary quantum state. So we cannot apply this on quantum computation. Why? Because we have the no cloning theorem. That's one reason. The second reason is that all classical errors boil down to bit flip errors. So classical errors all boil down to bit flip errors. So ultimately, they are based on bit flips. Whereas in quantum computing, there are continuum many errors. In QC, there are continuum many errors. We will see why. And then third reason that we cannot apply the repeating state solution is because whenever we measure a quantum state, then our quantum system gets collapsed. So the quantum state gets projected onto one of the basis states, which causes us to lose information. So measurements on quantum state lead to collapse of the state. So this is why we cannot easily apply the repeating state solution on quantum states. But despite all of these limitations, these handicaps, it is still possible to overcome these issues if we model the error, the type of error. Okay. So in classical computation, theory of classical error correction consists of 3 stages. there are 3 stages in error correction. First stage is to characterize the error model. Okay. First, characterization of the error model. Error model means that what type of error that bits are affected by. And second is introducing some redundant information through encoding. So its second step is the encoding stage. Encoding. And this will likely to produce redundant information, similar to that when we recall that we introduced auxiliary wires when we tried to make the computation reversible. So this is something similar. This introduces redundant information. And third and final step is the recovery procedure, the decoding step. Okay, so we start with the error model, characterization of the error model. This is the first step in protecting our information. So simply to define, an error model describes the evolution of collection of bits. Okay, and most of the times errors occur during the transmission of the bits, right? During the transmission. So when the bits or collection of bits are transmitted through channels, we usually assume that channels are faulty, because idealized channels are only, it can only happen in idealized closed systems. Okay? But in physical quantum computing machines, we always have faulty channels on which errors could occur. Okay, so the error model. So, of course, an error-free channel is an identity channel, a channel on which no transformation is applied to change the bits, but we assume that the channel is faulty. So there's some error operation, some transformation going on the channel during the transmission. Okay. All right. So we begin with a very simple error model called the bit flip error. The bit flip error. So the bit flip error works as follows. In the bit flip model, the state of a bit is flipped with probability p, and it remains unaffected with probability 1 minus p. So if we are in state 0, then with probability p, the state will be mapped to 1 with probability p, and with probability 1 minus p, it will remain the same if we are lucky. 1 minus p. And if we are on state 1, then the error channel will map this state to 0 with probability p, and it will remain the same with probability 1 minus p. Okay, so this is the classical bit flip channel. Or bit flip model. All right. So we could have a collection of errors, in fact, not just one error, but we could also have more than one errors, a collection of errors. And each error could be denoted by an index. So let's suppose that we denote each error by epsilon I, okay, classical. C indicating that the error is a classical error, acting on classical bits. Okay, so we have a collection of errors, epsilon I, each occurring with probability pi, let's say. So this could also be the case, that we could also have more than one error acting on the transmission channel. Okay. All right. So the next stage is the encoding stage. So the encoding stage is that once we have the description of the error model, such as the one above, the classical bit flip channel, if we know the error model, then we could encode our bits in such a way that we could recover them later, even if they're introduced through a faulty channel, okay, assuming that we know the error model. Now, this could be done by adding extra bits to our collection of bits that we want to protect, and then we produce a logical bit. Okay, so this is actually the encoded bit. So we encode our collection of bits and obtain a code word. Code word means encoded bits. So the original bit coded in coded as a code word, okay, in an encoded form. Right. So of course, as in the repeating state solution, we could have introduced redundant information here, right? So the next two bits are redundant in this case. Okay, so of course it should be noted that we encode the bit or collection of bits that we want to protect prior to any occurrence of the error. So we need to encode the string or the bit that we want to protect before they get introduced to the faulty channel. Okay, so if we have n bits of information, right, and it could be encoded by adding, say, m many ancillary bits. So suppose so I think there's a problem with the pen. Oh, there you go. Okay. Right, so suppose we have n bits. And now we encode this bit, this sequence, so encode this sequence and obtain, say, a code word of length n plus m. So if we introduce m many ancillary bits, then we will have a code word of length n plus m. So if B is the bit that we want to protect, so let me call this original bit. Original bit that we want to protect. And encoding process introduces a code word, B encoded. So this is the code word for B after the encoding operation. Okay. So encoding operation simply takes the original bit or a sequence of bits, and it applies the encoding function, possibly by introducing auxiliary bits or ancillary bits, and obtain a code word for the original bit. So the third step and the final step is the error recovery procedure. Error recovery. Now, after introducing the code word to a faulty channel or to the error model, then it'll get corrupted. Like so benc, by introducing this to our error model, so the output then will be some corrupted bit B star encoded. Okay. But then we apply the error recovery procedure. The error recovery procedure, and then we obtain our original bit. Along with some auxiliary bits here, okay? Maybe set to 0. Okay, so what we do overall is that we have a collection of bits that we want to protect. Okay, sequence of bits B, and then we have some auxiliary bits set to maybe 0 initially. And then we introduce them to the encoding procedure. Okay. And then what happens now here, that the encoding function produces a code word for B. So this is benc, B encoded. And then we introduce the code word to our error model, error, possibly classical, or we will cover quantum errors shortly. And then after the error we have a corrupted code word, B star encoded. And then finally we have the recovery procedure, decoding or recovery. And then obtain our original bit, along with some bits of zeros. Now, one important thing to mention is that the recovery operation must be able to uniquely distinguish between code words after errors have acted on them. Okay. Now, if we assume that we have a collection of errors, each denoted by, say, epsilon I C, okay, so we have a collection of errors, then we want to ensure that for all k, and L, so for distinct k and L, we want to ensure that epsilon I, the code word obtained from k encoded, should not be equal to epsilon j L encoded. So otherwise this wouldn't work. right? So this is the condition for error correction. Okay, so this essentially says that when any error acts on two different code words, the resulting strings are never equal. Okay, so I'll see you in the next video.